Okay? So if your curve is closed, then we can use this integral sign to indicate this curve is indeed closed. Okay? You have a small circle around your integral sign. That is indicating the domain as the curve is a closed curve. Okay? So I want to practice a couple of examples. Okay? So let's first look at this guy. So C is a circle of radius 8 centered at the origin and also orientated counterclockwise. This is a pretty long word, so to save me some energy, I'm using CCW for counterclockwise. Okay, counterclockwise is the default direction or orientation we choose for all the curves. Okay, but to be precise, I always mention the orientation as well. So I want to compute the line integral of this guy. I want to compute this guy. Okay, so what is the answer here?
0.
It's going to be 0. In order to verify this is indeed 0, the only thing you need to do is to check whether this vector field is conservative or not. Right? You have to check whether this is conservative or not. If it is conservative, then we can take the symmetric partial derivatives. X derivative with respect to y is equal to 0. Y derivative with respect to x is also 0. So this is indeed a conservative vector field. Equivalently, as long as the vector field is conservative, you can find its potential, right? You can find its potential function. What is the potential function for this guy? I want to have x squared divided by 2. I also want to have y squared divided by 2. And there's a constant coming out. This constant is not going to be important when you evaluate the function difference, just as what we did in the single variable case. Right? You can stick in any constant here, but they're going to cancel out when you take the difference of the function values. So this is the potential function of this conservative vector field. And then as long as the curve is closed, which is indeed the case right here. I have a circle, so it's closed the curve. Then this guy has to be equal to 0. But also, I want to remind you of how to take line integrals. I want to remind you of how to take line integrals for several reasons. First reason, I want to check whether my fundamental theory of calculus is indeed valid. Second thing is, there are a lot of vector fields which are not conservative. You still remember what we mentioned about in the very beginning. Conservative vector field is a very, very special class of vector fields. Only the conservative vector fields, the line integral of a closed curve is equal to 0. If it is not conservative, or if it is not closed, then you have to do a whole bunch of things. Are you with me? Mm-hmm. So I have to also remind myself or you guys of how to find the line integral. So how to find the line integral? How do you find the line integral of a vector field along a curve? So Brian, get any idea? So what's the keyword I'm looking for? I have to have this parametric form to begin, all right? No matter what line integrals you're doing, you have to have a parametric expression of whatever curve you have. Are you with me? Without this parametric form, there's no way you can even begin your evaluation of line integral. You have to have this parametric part, which means I want to have a parametric or a parameter t, and this is a curve, which means it's a pretty easy part. What is the parametric equation for this circle? Radius 8, centered at the origin counterclockwise. This is pretty much our favorite object. Right? So that is
cosine
t and
sine
t. And it is counterclockwise. You can check, this is indeed a counterclockwise. And also, I want to have a restriction on my parameter t here. If it is a whole circle, I want to have 0 to 2 pi. Okay? I want to have 0 to 2 pi. Then the way of computing this part, is to stick in your parametric equation everywhere, right? That's pretty much it is. You have to, of course, compute the derivative of the equation, right? So this is the tangent vector, which is essentially the derivative of the parametric equation, all right? You guys seem confused here a little bit. So I want to have from 0 to 2 pi. Remember, we have 2 steps to stick in our parametric equations. But indeed, if you are smooth about it, you can do it in 1 step. F is equal to xy, so I only have cosine t, sine t here. Am I right? Mm-hmm. Yep.
Isn't if the circle's radius 8?
Mm-hmm. Oh, sorry, I have 8 here, and I have 8 here as well. Yeah, thank you. So xy is equal to 8 cosine t and 8 sine t here. Okay? And then I have to multiply by the derivative of this function. What is the derivative for this function?
Negative.
Minus 8 sine t and 8 cosine t. So the dot product between the vector field and the tangent vector of the curve. And then I'm taking the derivative, the integral with respect to t. So if you expand what is inside, you have a minus 64 cosine t, sine t, and then you have a plus 64 sine t, cosine t. And they cancel out. That's why in the end I get a 0. Okay? They cancel out. So in the end I get a 0. So indeed, for the simplest example ever, I actually verified the fundamental theory of calculus in a case where the curve is indeed closed. So the closed curve conservative vector field is always equal to 0. So I want to give you one more example to practice our fundamental theory of calculus of conservative vector fields. So I have this vector field. F is equal to x, y, and z. So this RT is given by cosine t, sine t, and t divided by pi, where t goes from 3 pi divided by 4 to 7 pi divided by 4. So I want to compute CF, the line integral of this vector field with respect to curve. First of all, I'm not sure whether this curve is closed or not. So I don't use the notation over there with the small circle. So it's just a usual line integral. Okay? It's just a usual line integral. Second, even you don't know what a conservative vector is, you have no idea what fundamental theory of calculus of conservative vector fields is, you can still compute this line integral. Right with me? You can still compute this line integral. What is this curve? What is this curve? It is a circle in xy. In xyz, this is pretty much the 5th or 6th time we're looking at this kind of curve. So z is increasing linearly. Xy are sticking with circle. So this is a helix. So it is pretty nice to begin from xy. Xy is going to be restricted on a circle, central at the origin with radius 1. And then z is increasing linearly. So essentially, you are breaking down a circle and pull it in the z direction to form a helix. You know what I mean? This is basically how you can see this spring looking like shape. So let's compute whatever line integral is required to do. Okay? And then we can use our fundamental theory of calculus and see what we can simplify it. So if this is the curve, what we have here is going to be cosine t, sine t, and t divided by pi. This is my vector field right here, right? The vector field is x, y, z, so I'm using this curve, the parametric equations, to stick in this x part, y part, and z part, and get this whatever vector field it is in terms of D. That with me? So I want all of you to be clear what we're doing here. Okay? And then I have to inner product with the tangent vector. Tangent vector of this parametric equation. All right? So the tangent vector is with respect to t. What do you have? Minus sine t, cosine t, and 1 over pi. Okay? I want to stress it again. Here, this is the vector field. Here, this is the tangent vector. Okay? Tangent vector. And then I'm taking the line integral to a simple integral from 3 pi over 4 to 7 pi over 4. Okay? So taking the line integral, the key step is to represent your curve in parametric form. If your equation or the problem already provides you what the parametric equation is, the evaluation part is pretty straightforward. You just need to stick in the x, y, z for the function, vector field, and then the derivatives for the curves in the tangent part. Okay? And this is indeed from 3 pi divided by 4, 7 pi divided by 4, what we have here? Minus sine t, cosine t, plus sine t, cosine t. So luckily this part will be canceled out. And then we have plus t divided by pi squared. And the whole thing taking the integral with respect to t. And I myself actually did this computation. This canceled. I'm just taking the line or the single variable integration with respect to t divided by pi squared. And this arithmetic is pretty simple. So I'm going to do it for 5 divided by 4. That's the number name. This is the number name. And in last week, we actually gave explanation of what this number is actually telling me. Do you still remember that? So this pulling a train explanation. So if you have a curve and any moving object is restricted to a curve, and you're pulling this object according to this vector field as your force, then the total work you're done within this whole curve is going to be 5 divided by 4. All right? So in the beginning, if your object is not moving at all, then at the end, it's going to be moving in a kinetic energy of 5 divided by 4. Okay? And of course, in physics, you have to stick in all the correct units in order to make it work. But I know by fundamental theory of calculus, if this vector field is conservative, which in this case it is conservative. This guy is conservative because I can easily write down the potential function, which is equal to half of x squared plus y squared plus z squared. All right? So this is the potential function plus the constant c here. Right? So if you want to check whether this is indeed the potential function, you take the x derivative, y derivative, z derivative, they're all fitting over there. So this is indeed the potential function. And because it is a conservative vector field, taking the line integral with respect to any line, it is just equal to the function difference at the beginning point, sorry, at the terminal point minus the function value at the initial point. So f dr. Okay, which is just equal to this guy, which means I just need to figure out where this curve is beginning at and where it is ending. That was me? Are you clear what we're doing here?
Yeah.
Okay, so A here is going to be R of 3 pi divided by 4. Am I right? A is the initial point where I have to stick in my initial time 3 pi divided by 4, which means I have to evaluate cosine 3 pi divided by 4, sine 3 pi divided by 4, and also 3 pi divided by 4 and then divided by pi. What is cosine 3 pi divided by 4? Cosine 3 pi divided by 4, this is my curve. this is my curve, this is pi. 3 pi divided by 4 should be right here. It's going to be minus square root of 2 divided by 2, right? Minus square root of 2. One way you can understand it or find these trigonometric values is to go back to the trigonometric curve. If you are not familiar with the curve, 3 pi divided by 4 is actually right here, all right? And the cosine value is x divided by the hypotenuse. X is minus 1, then you can make this guy to be square root of 2. So that's why you have minus square root of 2 divided by 2 here. So sine 3 pi divided by 4. What's the value here? I already have the trigonometry here, so it's going to be square root of 2 divided by 2. Or if you want, you can have a sine curve which goes like this. All right? 3 pi divided by 4 is actually here. So it's going to be a positive square root of 2 divided by 2. And I have a 3 divided by 4 right here. Okay? So my initial point is this guy. So my terminal point is going to be r evaluated at 7 pi divided by 4. Which means I have to evaluate cosine 7 pi divided by 4, sine 7 pi divided by 4, and 7 divided by 4. What is cosine 7 pi divided by 4? Cosine 7, still you can use the curve or the actual triangles. All right? If I go for a curve, 7 pi divided by 4 is just slightly smaller than 2 pi. So it's going to be here. So my cosine value has to be square root of 2 divided by 2. All right? So sine 7 pi divided by 4, I'm going to go for here. So it's the minus square root of 2 divided by 2. And 7 divided by 4. That's my terminal point. Okay? So I find the initial point, I find the terminal point. Then I plug in what is in here, so it's going to be half of minus square root of 2 divided by 2 squared plus square root of 2 divided by 2 squared plus 3 divided by 4 squared. Oh, sorry. That's my initial point. I want to have the terminal point, so it's plus. So I have a minus, and also I have a 7 divided by 4 squared. So this is your potential function evaluated at the terminal point. And then minus half of